Yeah, so thank you very much, Katja and Knut, for the invitation. It's a great pleasure to speak in this already very established online seminar. So I will be talking about some recent results on inverse problems for wave equations. And these results are obtained by using a method which seems to be in some ways new. So we nowadays call it the plane wave method. So then my plan is to explain the idea behind this method and also the kinds of results that one has so far been able to achieve. So the results I will talk about are joint with Lauri Oksanen from Helsinki and Rakesh from Delaware. Some of them are still not available on arXiv, so we are finalizing those results. So there may be some small changes in the final statements. Okay, but so there will be three parts in these talks. First, I will give some motivation and introduce to some geometric inverse problems which lie on the background of these works. And then I will discuss some specific results for inverse problem for wave equations, also the Lorentzian wave equation, and state some of the main results. And in the third part, I will try to explain the method in some detail. Okay, so to begin, let me discuss, there is some notation. So one could pose our problems in domains omega and Rn. So we could be looking at, for instance, the Laplace equation, Laplacian equal to 0, or the conductivity equation, which is written here, where you have a matrix conductivity gamma jkx. And I'm going to somehow write this equation in geometric notation. So geometrically, I'm going to replace domain omega by a compact n-dimensional manifold M with smooth boundary. And this matrix conductivity gamma jkx, I'm going to replace by Riemannian metric G. And the Laplace operator will be replaced by the so-called Laplace-Beltrami operator, the canonical elliptic operator on the Riemannian manifold, which has this form in coordinates. So basically, it's an elliptic operator where you have a positive definite coefficient matrix, which looks very similar to the conductivity equation. And the benefit of doing this rewriting is that we can use geometric ideas and methods. A basic example would be the Euclidean metric, which is just the identity matrix, constant coefficient, and the Laplace-Beltrami operator would be just the usual Laplacian. Okay, so then I will discuss two geometric inverse problems. So IP will be an abbreviation for inverse problem. First one will be the Calderon problem, which involves an elliptic PDE. And the second one is an inverse problem for a hyperbolic PDE called the Gelfand problem, but it also has many other names. And okay, so what is the Calderon problem? It originally comes from electrical resistivity imaging in geophysics, where the purpose is to try to find, let's say, oil deposits inside the Earth by doing electrical measurements on the surface. So in the picture, you can see a field setup where you put these electrodes on the surface, and then you inject some currents into these electrodes, and there will be an electrical current flowing through the Earth, and then you measure somehow the resulting voltages on the boundary. And by repeating many measurements like this, you would like to determine if there are some oil deposits. It's also used in industrial and medical imaging. So the mathematical model is the conductivity equation, but written in a geometric form, it will be the Laplace-Beltrami equation. Laplacian G equal to 0 in M, U is equal to F on the boundary. So F is the boundary voltage, which is going to induce a voltage U inside the domain M to B image, which is solving the Laplace equation. So G now is the electrical resistivity, which is the inverse of the electrical conductivity. Okay, and the boundary measurements are given by the currents, which are the normal derivatives of the solution U, and then one can mathematically encode these boundary measurements by the Dirichlet-Neumann map, which takes a boundary voltage F into the boundary current, which is the normal derivative. And there's a footnote here, which I will use a little bit later. So this data, the Dirichlet-Neumann map, is actually equivalent to mathematically to the so-called Cauchy data set, which just encodes all the Cauchy data of all harmonic functions in your medium M. The inverse problem Calderon is given the boundary measurements lambda G, you would like to recover G. And Calderon originally posed this problem in Euclidean space with a scalar conductivity. But if you have a matrix conductivity, which would be the anisotropic Calderon problem, you would essentially get this formulation. Okay, so just to repeat, given the Dirichlet-Neumann map lambda G, which gives you the boundary measurements, you want to recover the conductivity G. But you can only recover it up to gauge. So gauge means, in this case, some natural invariance that you have in this problem. And in this case, because the Laplace-Beltrami equation is coordinate invariant, it doesn't really matter in which coordinates you write this equation. You can already recover the matrix G up to a coordinate transformation. So precisely, you want to show that if lambda G is equal to lambda G0, you want to show that G and G0 are the same up to some change of coordinates given by a differential motion, which fixes the boundary. So all the results of recovering metric will mean that I want to recover a metric up to this kind of differential motion gauge. Okay, so this problem for matrix conductivity is the anisotropic problem is well understood in 2 dimensions, but in 3 and higher dimensions, it's known only in some special cases if the metric is real analytic due to Lasses and Ullmann, or if this metric has some kind of product structure. So you can see here that the metric is a conformal multiple of dt squared plus h of x. So in some sense, the metric is independent of the t variable. In particular, it's real analytic in the t variable. So if you don't have this real analyticity or product structure, then it's a major open question. So what we are going to look at in this talk is a wave equation version of this problem. So I call it the Gelfand problem because an equivalent version of this problem was posed by Gelfand in the 1950s. And this problem could come up, for instance, in exploration seismology. So you have geophones on the surface of the Earth, and you create some somehow noise, some controlled explosions. So you have some configuration of explosions, and then these are going to generate waves which are going into the Earth, and they are going to reflect off of some structures in the subsurface, and then you're going to listen what comes up. Or I guess in this picture it's actually the this kind of vehicle which is making the explosions, and the geophones are listening to what comes up. Right, so mathematically this is modeled by the wave equation. So now you have this kind of, let me show you this space-time cylinder. So you have kind of your domain to me image could be the Earth, for instance, which is modeled by Riemannian manifold Mg. And then you are imposing a Dirichlet data F on the boundary of your domain for some time, capital T. And then this is going to generate the wave u, which is all in the wave equation, dt squared minus Laplacian gu. And what you measure on the boundary is the normal derivative of the solution. So in this case, the boundary measurements are encoded by the hyperbolic Dirichlet-Neumann map, which takes a Dirichlet data on the lateral boundary of the space-time cylinder and takes it into the Neumann data. the inverse problem is given the hyperbolic Dirichlet-Neumann map, you would like to recover the sound speed given by the Riemannian metric G, again up to diffeomorphism motion, which fixes the boundary. Okay, and so we can also look at this problem from a slightly different angle. So this wave operator dt squared minus Laplacian G is actually the same thing as the wave operator for a special Lorentzian metric H, which is equal to minus dt squared plus g of x. So this is the kind of thing which comes up in the theory of relativity, where you look at space-times described by Lorentzian metrics. So this is kind of saying that if you have a Lorentzian metric which has special product structure, which is very similar to the product structure which we already had in the standard Calderon problem, then we get the Gelfand problem. But in the anisotropic Calderon problem, we would like to get we would like to look at general somehow metrics which don't necessarily have product structure. So in this case, the true hyperbolic analog of the anisotropic Calderon problem would be the following. You ask if the hyperbolic Dirichlet-Neumann map for a general Lorentzian metric, does it determine the Lorentzian metric H? So this will be kind of the question that we will be looking at. And okay, so these wave equation problems are quite classical, and there are many methods for trying to solve them. And let me mention some, let's say 3 methods for which one can get uniqueness results. So there's the boundary control method, the geometrical optics method, and then this new one, which we call the plane wave method. So what are these? So all of these, you can think they employ some kind of special solutions to the wave equation. And the boundary control method has these types of special solutions. So I haven't written down all the definitions here, but the idea is that we have some subset capital gamma of the boundary, and then this M of gamma t is the domain of influence, which is the set of all points in the manifold which can be reached from the boundary path gamma in time capital T. And because the wave equation has a finite speed of propagation, then the solution U for Dirichlet data, which are supported in gamma, has to be supported in the domain of influence. And then the special solutions used in the boundary control method are roughly those where you can basically make the solution at the fixed time capital T to look like almost like any L2 function in the domain of influence. So you can control how the solution looks at the fixed time inside the domain of influence. And this fact that you can control the solution is obtained by duality from Tataru's optimal unique continuation theorem. So once you have these things, you can start the boundary control method, which allows you to determine the metric in certain cases. For instance, in case where you have a product structure. So this is the original setting, of course, of the Gelfand problem. And the method was introduced by Belishev, and many other people have worked on it. It's a very somehow refined method nowadays. It also works if you assume real analyticity in time, because Tataru's unique continuation is valid if you have real analyticity. This is work by Eskin. But in general, Tataru's theorem fails if you drop the real analyticity assumption. So it's interesting that even though this is a wave equation problem, is different from the elliptic Calderon problem, but still somehow you have the same kinds of obstacles. So you need to assume either product structure or real analyticity to do things. So there's one exception. There's very nice recent work by Alexakis, Faiz, Mohammadi, and Oksanen, who were able to prove basically a version of Tataru's optimal unique continuation theorem without assuming real analyticity, but replacing those with some Lorentzian curvature bounds. Okay, so that's quickly about the boundary control method. the next method is based on geometrical optics solutions. So these are special solutions which have this form, let's say U equals e to the I lambda phi a, where lambda is a very large frequency, and these solutions strongly concentrate near null geodesics. So if you look at this picture here, somehow these black lines are supposed to mean null geodesics for some Lorentzian metric. If you have, let's say, a constant coefficient metric, these would be the straight lines, which make this 45-degree angle. But if you have a variable coefficient, then you get something like this. And the idea is that if you can make a measurement of a geometrical optics solutions, then let's say if you look at this null geodesic, then you can recover, let's say, some integral of an unknown coefficient along this null geodesic. And in this way, by using geometrical optics solutions, you can recover things like a scattering relation, which means that you know how these curves somehow come out of the domain, or you can recover a light ray transform, which is the integral of some unknown coefficient along these curves. And then you would be able to solve the inverse problem if you can, for example, invert the light ray transform. But unfortunately, there you still have the same obstacles. You either need some product structure or analyticity. And this is somehow understood already from basically the first invertibility result for the light ray transform by Stefanov, which was showing that if you know the integrals over straight light rays, then you can recover the Fourier transform with the function in some cone or in some conic set. But there are some frequencies of the Fourier transform which are missing, and those you need to fill in by analytic continuation. So that's why real analyticity is needed. And this geometrical optics method goes back to work by Rakesh and Symes in the 1980s. And again, many other people have contributed to this and also to the study of the light ray transform. Right, so what is the new method? It's the plane wave method. It also uses certain special solutions, and these special solutions will be distorted plane waves. And these are simply functions which are delta functions of hyperplanes. So you are basically sending a delta function of a hyperplane from far away, and it's propagating in some fixed direction omega. So here you have this kind of a hyperplane, and then you have this hyperplane, or the delta function of this hyperplane propagating in direction omega. At some point, it's going to enter a region where the coefficients are not constant. And then if you have a metric, then the plane wave is going to bend. You might get something like this at some later time. So you're going to take these kinds of solutions, and then you are going to measure what comes out. And I guess somehow this method in the form that I'm going to describe goes back to my work with Rakesh on the fixed angle inverse scattering problem from 2020. But it seems that it can be used for many other problems besides the original one. So I'm going to talk about some subsequent work also with Oksanen. And some benefits of this problem is that this method does not seem to be sensitive to real analyticity. So it seems to work for, at least for certain smooth time dependent metrics. I'll explain a bit later which metrics it works for. And also you don't need the full Dirichlet to Neumann map, unlike in the earlier cases, but you can get uniqueness results with much smaller formally determined amount of data. And also in some cases, this method is even Lipschitz stable if you measure things in the right Sobolev norms. In other cases, we have not proved stability, but it seems that in cases where this method works, it seems to give stable reconstructions. And this is somehow a method uses these special solutions, the distorted plane waves, and also some unique continuation and Karlemann estimates via some modification of the Buchheim-Klibadon method, which is one of the important methods for dealing with formally determined inverse problems. Somehow in many somehow rigorous settings in the Buchheim-Cleverdon method, you either need interior sources or interior measurements. But we have some version of this method in which you can just send sources from the exterior and measure things on the boundary and still get some results. Okay, but I guess this concludes the motivation part. Are there any questions at this point? Okay, if not, let's go to the second part. I will state some of the results that we have obtained. So we are going to talk about Lorentzian wave equations. So H will be a Lorentzian metric in the space-time which is as R1 plus n. So it means that it's a smooth symmetric matrix function where always one eigenvalue is negative and all of the other eigenvalues are positive. The basic example is the Minkowski metric H min, which is just the matrix where you have -1 in the upper left corner and then you have the identity on the lower right. And for any Lorentzian metric, there is a canonical wave operator, which is whose local coordinate formula is written here. It's exactly the same formula as for the Laplace-Beltrami operator, but now one of the eigenvalues of this matrix H is negative, so this is actually a wave operator. And the wave operator of the Minkowski metric is dt squared minus Laplacian of x. I might be missing a sign in my definition of the Lorentzian wave operator to have that, but yeah, but that's some other Minkowski wave operator. Okay. And so I'm going to state the first result, which is a local uniqueness result of the following form. So our space-time is R1 plus m, and we have some bounded domain m, and in R1 plus n, and then we are going to look at the hyperbolic Cauchy data set, which is the set of Cauchy data of all, let's say, C infinity solutions of the wave equation box HU equal to 0 in M. So this is just the hyperbolic analog of the Cauchy data set in the usual Calderon problem. And the theorem is that there is a positive epsilon such that if you have two metrics H1 and H2, which have the same hyperbolic Cauchy data sets, and if both of them are epsilon close to the Minkowski metric in the C3 norm. So, okay, so then these metrics have to be the same up to diffeomorphism. So it's somehow saying that if you take any two small perturbations of the Minkowski metric, and if they have the same boundary measurements, then they will be the same. So some features of this theorem is that it applies to arbitrary smooth metrics, so you don't need to assume this product structure or real analyticity as long as they are sufficiently close to the Minkowski metric. The proof is based on the plane wave method, and it's interesting that the corresponding result for the classical anisotropic Calderon problem is still very much open. So it's not known even if you fix one of the metrics to be Euclidean, you cannot distinguish the Euclidean metric from a small perturbation of the Euclidean metric in the standard Calderon problem, unless you assume some real analyticity. But now, at least for the Lorentzian version of the Calderon problem, we can get such a result. And this theorem is actually a consequence of a more general result, which we call a semi-global uniqueness result. In particular, this means that that both of the metrics don't need to be close to the Minkowski metric. Only one of them needs to be close, and the other metric can be more general. So let me try to state this more general result. And in order to do that, I need to discuss one assumption, which is the global hyperbolicity. So somehow, in order to construct the plane wave in R1 plus n, we need to be able to solve the Cauchy problem, which can be, for instance, stated in this way, that you want to be able to solve box HU equal to capital F, and U is equal to 0 when time is large and negative. And of course, any reasonable space-time should have this property, but one can construct counterexamples. For instance, if you have a space-time where you have time loops, so where time travel is possible, so you start at one point in space-time, and then you travel into the future, and then let's say travel back in time, and then you come back to the same point in space-time, then this would invalidate the solvability of the Cauchy problem. But there is a standard condition for well-posedness of the Cauchy problem, which is global hyperbolicity, and the definition is written here. It may be a bit complicated, but it just means that there is a smooth function which serves as a global time coordinate. So the level sets are Cauchy hypersurfaces. But this is in some sense not a very stringent condition. Any reasonable space-time would satisfy this. And once you impose global hyperbolicity, then the Dirichlet-Neumann map lambda H hyp is well defined. Okay, so this is the second theorem. It's semi-global uniqueness. And now, so we are looking at two metrics, H0 and H1, and we make two assumptions. So they both are smooth Lorentzian metrics in R1 plus n, and they have to satisfy this globally hyperbolic condition, which ensures that plane waves exist, and they have to be equal to the Minkowski metric outside the compact set. So you have some compact region, which is this one here, and outside of this compact region, both of these metrics have to be the Minkowski metric. And then you put some conditions on the metric H0, so all in one of these metrics. So there's three conditions, which I will explain on the next slide, but they are called directional simplicity, iconal gauge property, and the spanning condition. So if one of the metrics H0 satisfies these conditions, and H1 is some other very general metric, and if the boundary measurement for H1 are the same as those for H0, then H1 has to be equal to H0 up to this diffeomorphism. So, okay, so I should explain these three conditions. So first of all, this extends our earlier rigidity result, which was stating that if you assume that the other metric H0 is exactly the Minkowski metric, then we had this kind of result. But now we can prove it also for H0, which are more general than the Minkowski metric. So these three conditions informally mean the following. So this directional simplicity means that the parallel null geodesics smoothly parameterize M. So this is maybe a bit difficult to visualize in the Lorentzian case, but in the simpler case of a Riemannian manifold, this just means that if you look at the set of parallel geodesics, which are all starting on this hyperplane down here, and which are all starting in the same direction omega, then if you follow these geodesics, they will smoothly parameterize your domain M. So this means that you cannot have caustics, so you cannot have this family of parallel geodesics somehow converging to a caustic point. Right, so condition 2 was an iconal gauge property. It just means that there exists some n+1 solutions of the iconal equation h naught of d phi equal to 0, which give you a global coordinate system near your region M. And finally, the spanning condition means that you have somehow the set of these iconal solutions phi is so rich that the span of these matrices d phi tensor d phi is the set of all symmetric matrices at any point. So these are a little bit maybe not so easy to visualize, except for the first one, but let me just say that any small perturbation of the Minkowski metric satisfies all of these. And in some sense, one might think that condition 1 is the most important, because this condition 1 implies some weak versions of conditions 2 and 3. So the simplicity condition is maybe the most fundamental one. Right. Okay, and this iconal gauge property, let me explain that a little bit more. So what does it mean? So the idea was that we have some natural invariances in many geometric inverse problems, and in these problems that I'm talking about, the invariances by a change of coordinates. So one might somehow try to solve this issue of non-uniqueness by gauge, by fixing the gauge. So you might choose some very special system of coordinates where you're looking at things and try to recover things in those coordinates. So in the setting of Riemannian manifolds, a popular gauge for geometric inverse problems has been the normal gauge, which means that basically that you want to recover, let's say, a Riemannian metric in boundary normal coordinates. So this has been used in the Calderon problem, also in boundary rigidity. Of course, the problem with this normal gauge is that the boundary normal coordinates only exist in some neighborhood of the boundary, and then you may need to do some non-trivial work to extend this gauge all the way to the interior. And this is what Lassas and Ullmann did, for instance, in the Calderon problem. Another possible gauge is the one which comes up in the boundary control method, where you are looking at coordinate systems given by boundary distance functions. And a third one, which has maybe not been used that much, would be the harmonic gauge. So you might want to recover your metric in some coordinate system where each of these coordinate functions is harmonic. And in our case, we have a wave equation, so we would have the wave gauge where the coordinates solve the wave equation. And this actually would be a convenient gauge, but for technical reasons, we have to use this fourth gauge, which is called the iconal gauge. So we want to somehow fix a coordinate system where all of the coordinate functions solve not the Laplace equation, but the iconal equation. So they are distance functions and certain types of distance functions. And for instance, if you have the Euclidean metric, you could just take the usual Cartesian coordinates, and these solve both the iconal equation because the gradient of xj is equal to 1, and they are also harmonic. So this would be the kind of gauge that one could use for the Euclidean metric. Okay, but I think this concludes the second part of the talk, which was the statement of main results. Any questions here?
Can I just ask one question, Mikko? In your theorem 1, do you also assume that H0 and H1 are Minkowski outside of some compact set, or?
No, we don't. But we do assume that our manifold M is a subset of R1 plus N. And then because both of these metrics are close to Minkowski, you can extend them in such a way that they will be Minkowski outside some slightly larger compact set. So one can reduce to that setting.
I see. Thank you.
Thanks. Other questions? Okay, so let's then go to the third part, which is trying to explain in a little bit more detail this plane wave method. And so the method, it gets a bit involved, so I'll try to explain it in some slightly simpler situation first. So for now, I'm going to forget about the Lorentzian setting, and I'm just going to look at the MG, which is a compact Riemannian manifold with boundary, and I'm going to explain it for the case of the wave operator dt squared minus Laplacian g in this space-time cylinder 0 t cross m. And I'm going to do it first for the rigidity result, where one of the metrics is assumed to be exactly the Euclidean metric. And then I'm going to, if there's time remaining, I'm going to explain how to extend it to the case where this other metric G0 can be something more general. So let's see how this goes. So what are these plane waves? So let me draw some pictures to give you further insight. So omega is a unit vector in Rn. It will be the direction propagation of the plane wave. And then we are looking at the plane wave u omega of tx, which is, in this case, it would be the heavy side function of t minus x dot omega, which is solving the constant coefficient wave equation in R1 plus n. So you can think that there's this kind of a interface. The heavy side is equal to 1 on the other side of this interface, and it's propagating in direction omega. And now because the coefficients are constant, it's going to just stay as a straight hyperplane. But it's convenient also to draw pictures in space-time. So x will be on the right and t will be going up. And in space-time, the heaviside function, it will indeed be equal to 1 in the set where t is bigger than x dot omega. So it's going to be 1 here, and it's going to be 0 down here. So it's a very, very simple special solution of the wave equation. So what happens when you have variable coefficients? So if G is a Riemannian metric, you will have these distorted plane waves which are solving the wave equation with the variable sound speed in R1 plus n. And for negative times, they will be equal to basically the Euclidean plane wave. So this is the picture where you start with a straight hyperplane, and when it enters the variable coefficient part, then this interface is going to bend. So you can think somehow that each of these this interface is consisting of some number of wave packets which are pointing in this direction omega, and then each of these wave packets are following a geodesic of the metric, and then the bending of the interface will be according to that. And the space-time picture is similar. So in this case, outside of this cylinder, we have the Euclidean metric, so the interface is straight. But inside, we have some unknown variable coefficients, so the interface between 0 and 1 is going to be curved. And this interface here is some kind of interesting geometric information that we would like to use to recover things. Okay. And the theorem that I'm going to try to explain, the rigidity result, and this is from one of the earlier papers, which is already out, is saying that if G is a Riemannian metric in Rn, which is the Euclidean metric outside the unit ball, and then you are sending finitely many plane waves, and if you assume that the boundary data of the plane waves for the metric G are the same as the boundary data for the plane waves for the Euclidean metric for finitely many directions omega, then G is equal to the Euclidean metric up to this diffeomorphism. So certainly,
Mikko, can I ask you a question about the previous slide? So I really love your pictures. They are so beautiful. But now in this Riemannian case, so do you know that, what do you know about the interface here, which now here in the picture looks like a nice hypersurface? So is it always like this, or can it be somehow nasty looking in like fractal or something?
Yeah, I mean, certainly it can be more nasty than this. And the idea is that if you have these caustic points, then this interface might not be smooth. But we are going to make this assumption of directional simplicity, which rules out caustic points, and that implies that the interface has to be a smooth hypersurface. Thanks.
Thank you.
Right. Okay, so this is the theorem, and we indeed all use finitely many measurements, and this is a formally determined inverse problem, so maybe this is a good place to mention that there are other results for formally determined inverse problems. So there's this Puhkheim and Klibanov method, which in many cases assumes some interior measurements. But then there are other works where you have, let's say, some special source where you pack infinitely many sources into one, or you use some like a white noise source. And I guess I should mention here that Teemu Saksala, who asked the earlier question, has also done work in this direction. And there's very nice recent work by Ali Faiz Mohammadi and Katja Krupchik showing that if you have a source which excites all frequencies, then one might also be able to solve a formally determined problem. But our measurements are given by these plane waves, which are should be quite natural, at least from the mathematical point of view.
Mikko,
Okay,
if I
so
may interrupt, sorry.
Yeah.
So
Okay.
this is related to Teemu's question. So
Yes.
the point is that one of the metrics, we don't impose any of these simplicity conditions.
Yes.
Right. It's the other metric you're comparing with, which has the simplicity.
Yes.
So this is the question which, and as you will say later on, but I just wanted to let Teemu know that only one of the metrics is assumed to have that non-caustic condition.
Yeah, exactly.
Right. Okay.
Yeah, thanks. So I will actually get into that right away. So there's basically 4 steps in the proof of this theorem. So first, we use boundary measurements of plane waves to recover some scattering relation. So we call this single plane wave scattering relation of somehow the unknown metric G. And then we use knowledge of this scattering relation to show that this G has to be having this directional simplicity condition. So this is exactly what Rakesh said. So the Euclidean metric has the simplicity condition. And then because the metric G has the same boundary measurements as the Euclidean one, we are going to show that also G has to have the simplicity condition. So once you have that, then we get the very nice structure for the plane waves. So they will be co-normal distributions related to solutions of Eikonal equations. And then we eventually determine the metric up to diffeomorphism by using this Eikonal gauge and unique continuation property. Right, so the first step is the scattering relation, and here we are using some elements of the geometrical optics method. So the usual scattering relation alpha G is the map which takes a point X and direction omega on the boundary, follows the geodesic in that direction, and gives you the exit point and the exit direction. So this is a well-known object in the boundary rigidity problem. And the information that we get is only partial information on the scattering relation. It is single plane wave scattering relation. So we have this plane wave, we have geodesic propagating in some fixed direction omega, and then we are going to measure the plane wave when it comes out. So we know basically these points and these directions. So we know we send a bunch of, let's say, geodesics through the medium, and then we recover a bunch of exit points and exit directions. So we don't know which one they came from. We already recovered these things as a set, but these can be recovered from the waves from set of the plane wave, which we have access to from our measurements. And then the first theorem is that if G has the same single plane scattering relation as a set as the Euclidean metric, then G has to be simple in direction omega. And in the more general result, we get the same type of theorem, but this Euclidean metric can be replaced by a metric which has the directional simplicity property. Right, and just to recall, I already explained directional simplicity means that these parallel geodesics in direction omega parameterize our domain smoothly. And this is kind of similar to the standard definition of a simple manifold, which means that the domain is parameterized smoothly by radial geodesics. So the difference is that we are using parallel geodesics. So let me go on in the interest of time. So the third step is that because we have this directional simplicity property, then we know that the Eikonal equation, which is this one, norm of d phi g squared equal to 1, phi is equal to x dot omega in some region. This has a smooth solution in a large set. So if you look at this picture, we have the directional simplicity property. So this parallel geodesic smoothly parameterize your domain. And then it's well known that somehow these directions of these geodesics will be equal to nabla phi, where phi is the solution of the Eichel equation. Basic example, if you have the Euclidean metric, then you just take phi of x equal to x dot omega, and the gradient of this will have length 1. And this implies the structural condition for plane waves, they are co-normal distributions. In particular, they can be written as functions which are small u of tx, so there's some smooth amplitude times the heavy side of t minus phi of x. So the interface will be equal to the set where t is equal to phi of x, and u will be smooth in the region where t is bigger than phi. Okay, and then the fourth step is to determine the metric in some up to some diffeomorphism, and the idea in our earlier rigidity paper was that, okay, our plane wave is equal to some amplitude u times the heavy side of t minus phi. And now, because the boundary measurements of G were equal to the boundary measurements for the Euclidean metric, and then we use the fact that for the Euclidean metric, this amplitude u here is just equal to 1. And then the special property that the constant 1 solves the wave equation. And then we can look at this small u minus 1, use the unique continuation property to eventually get that this amplitude in this variable coefficient plane wave has to be identically equal to 1. And after substituting that back into the equation, you see that phi, in addition to solving the Eichel equation, it also solves the Laplace-Beltrami equation, which is a very strong constraint on phi. It turns out that from this argument that these functions phi, if you choose n functions of this type, they will form a coordinate system, and these coordinates could be called iconal coordinates or iconal gauge. And in those coordinates, we can show that G is Euclidean. Okay, so this is the rigidity result. And then I have some explanation on what happens when the other metric is not constant coefficient. So I won't have a lot of time to explain, but maybe just say a few words. Okay, so the rigidity result, we had a 4-step approach. And it turns out that if you want to get the uniqueness result, you want to change the other metric to something more general than Euclidean. Basically, the first 3 steps are the same, but the 4th one is going to change. So I'm going to go forward. And for this uniqueness result, it's not enough to use just the unique continuation property. We have to use somehow the quantitative tool. For proving unique continuous results, we need to use Karleman estimates in some kind of modified Buchheim-Klebanov method way. So just to explain this again, so for rigidity, we have that the plane wave is small u times the heavy side, and then the Euclidean plane wave is the constant 1 times the heavy side. And these two things have the same Cauchy data on the lateral boundary. So we want to look at this amplitude small u minus 1. And now, because this in the region where the plane wave is living, then this thing is solving the wave equation, and the constant 1 is always solving any wave equation. So the wave operator applied to u minus 1 is equal to 0. And this thing has 0 Cauchy data, so we're in a good setting to apply the unique continuation principle to get that u is equal to 1. So what happens when you have a variable coefficient? So then the first plane wave will be the same as before, and then the second plane wave will have some amplitude which is not anymore equal to 1. And also it will be living possibly in a different region because the somehow the Eichel solutions are somehow not the same. And then when you apply the wave operator to the difference of the amplitudes, you are not going to get 0. You are going to get something non-zero, some function capital F. So this is not a situation where you could apply unique continuation, but it turns out that this function capital F is related to, it's not just any arbitrary function, it's somehow related to the difference of the two metrics. And then you basically end up using a sequence of Karleman estimates with suitable weights in order to control some quantities in terms of some other quantities. But I still had a few slides about these Karleman estimates, but 50 minutes is already up, so maybe I'll end here. And if there are some questions, I can show still some of the other slides. So thanks very much.
Thank you very much, Mikko, for the very nice talk. Thank you very much. Are there any further questions or comments, please? Please feel free to unmute yourself. Any questions or comments?
Okay, I'll make one comment. Hi, this is Rakesh. So, I mean, Mikko and I work together, but we have slightly different slant on what we think we are doing. And so I'll give my interpretation of what we think are doing. The one difference between what we sort of call the plane wave method and the high frequency things, at least for the hyperbolic case, in the other methods, like the geometric asymptotic methods, I think one is using data only near the geodesics. Like you send in a solution, and your solution is going on a geodesic, and you measure the data on the boundary near the geodesic. And whereas for our situation, we not only use data there, but we use the other data. So like in some sense, the geometric asymptotics uses the singularity data, whereas what we use is data beyond that. So that's why we need only much fewer waves. And I think that's one of the major differences. And that's where the boogie method, the importance of the boogie method, Klebanov method, comes into play. So in some ways, in our methods, we have more data, like we have boundary data, but the geometric asymptotic methods do not use the full boundary data that is available. So that's my take on it. But anyway, I mean, people can disagree with that. So.
Yeah, thanks very much. I do agree. So we use a little bit of geometrical optics data by looking at the wavefront sets of these things and recovering scattering relations. But in addition to that, we use this PDE data, which is the full boundary data of the plane waves, and then we use Karleman estimates to control somehow to recover from the things on the boundary some things in the interior, especially on the interface of these plane waves, where there is some transport equation relating the solution into some of the unknowns.
Hi, Mikko. So can I ask one question?
Yes.
First of all, congratulations on this result to you, Rakesh and Laurie. It's a very nice result.
Thanks very much.
So one thing here, speaking of Rakesh's comments, I also thought always that these plane waves are equivalent to geometric optics, but it seems they carry also this finite speed of propagation, and there is something there, right? And I guess one of the points, maybe I haven't seen your Karleman estimates, but I guess on these characteristic surfaces, you get some positive boundary terms, right? Which is
exactly.
To some extent,
that would be the next slide. Yeah, so we are basically using Karleman on these kind of slanted cylinders. So this would be the lateral boundary here, and then this would be the interface where the plane wave changes from 0 to non-zero. And we are using Karleman estimate where you have a positive boundary term on this interface gamma.
Right, and this is quite important, I see.
Yes.
And then the second thing, somehow related to this, for this theorem 2, do you need to do these measurements at the final time also? Or do you
no. But there is kind of a catch. So maybe let me go back to theorem 2.
I guess because they're Minkowski, you can say somehow you get it for free, right, by unit continuation.
Yeah, that's exactly the case here. So we do assume that both of these metrics have to be equal to the Minkowski after some time. So So because of this, we can do some unique continuous results at some very large time to get some information for free, as you say.
And how about theorem 1? In that case, you're not assuming this assumption. Are you allowing measurements at the final time, or?
Yeah, in theorem 1, we have a bounded domain in space-time. So we kind of have measurements at the top here in some sense.
I see.
So we are implicitly using that.
Okay, thank you.
Thanks.
Thank you very much. Are there any other questions or comments, please? Any other questions or comments, please?
So maybe I can ask another question, Mikko. So you had this theorem where you said that you can basically say that if you have this single line scattering data, then you you see that the other metric also has to have this like directional simplicity if the other one has. So has this something a similar flavor than I think in this recent book by you, Günther and Gabriel, you have the result there which says that like a boundary distance function is simple if and only if the Riemannian metric is simple if and only the boundary distance function is smooth outside diagonal. So does this have kind of similar flavor that you could basically read this directional simplicity straight from this scattering relation?
Yeah, that's exactly the case. And this is actually the last 2 lines on this slide with this theorem. So the idea is that like in boundary rigidity, you can detect the simplicity of a metric just from the boundary distance function. We can detect the directional simplicity of a metric just from this single plane wave scattering relation. So it is exactly of that flavor.
But I would say there is one difference. Having the DG for all possible directions and all possible things is not the same as having it for just one direction.
Yeah,
so,
that's correct.
Right. So there's one big difference there. So our result says that if you have 2 metrics and one is simple in one direction and the boundary data agrees, meaning the wavefront set, then the other one is simple in that direction. So it's a little different in nature. I'm sorry to say this, but it's not like knowing DG for all possible boundary points kind of thing.
Yeah, that's right. So it is somehow kind of philosophically similar, but it's a different situation. We only have partial information on the scattering relation, and we only get some partial knowledge on the metric in return. Thanks.
Thank you very much. Are there any other questions or comments, please? Any questions or comments, please? Any other questions? Okay, if not, thank you very much, Mikko, for the very, very nice talk. Thank you so much. Thank you very much, everyone, for coming. Thank you very much.